Hello, my name is Arnaud and today I will present you a new particle-based liquid control system using precomputed liquid animation templates in order to compose art-directed liquid animations. It is commonly known that the motion of most fluids in computer graphics is ruled by the Navier-Stokes equations. Researchers have proposed many methods to approximate a solution to these equations in order to simulate various types of smoke and liquid in a physically accurate way. However, artists may want to step away from a purely physically accurate behavior when designing an art-directed targeted animation. Although art-directed, such an animation has to look plausible and should therefore follow as closely as possible complex fluid-like motions usually obtained by simulation. Finding a good trade-off between a purely physically accurate simulation and a completely scripted implausible animation is a challenging research topic that has been actively investigated for more than 15 years. Several methods performing a numerical optimization to drive a fluid in order to make it match a given target have been proposed in the past. McNamara and colleagues perform a spacetime optimization in order to control either a smoke or a liquid to match a small set of keyframes. Pan and colleagues locally edit a low-resolution liquid simulation by solving an optimization problem on a subset of particles. Some systems propose to compose a liquid simulation using a database of animation sequences. Mihaljev and colleagues generate controllable wave simulations using a library of breaking waves. Monteau and colleagues sculpt a mesh extracted from the surface of a liquid simulation using a database of pre-recorded liquid meshes. Thuret and colleagues use control particles to generate forces in order to control a liquid. These forces are applied to the low-frequency component of the velocity field. The method is efficient since the control applied in a region of space only depends on its control particle neighborhood. Boschen-Hansen and Vosstein insert template liquid animations into an existing fluid simulation using spatial boundary conditions to smooth out transitions. The method locally edits a region of precomputed liquid without affecting the rest of the surface. Therefore, newly generated waves and splashes do not propagate outside of the control region, which can be an issue when designing a complex liquid simulation with many parts interacting together. Stomakin and Sell introduced the flux animated boundary method. This method uses an input control shape and a material flow field to enforce boundary conditions and recede particles around the shape describing the open boundary of a flip simulation. Our goal is to develop a system to compose a particle-based liquid simulation using liquid animation templates. We want our system to be intuitive and easy to use for an artist with little knowledge in physics, provide efficient control to give quick visual feedback during the design process, generate plausible liquid animations, and be compatible with various targets in order to generate a wide range of simulations. As said earlier, our system is based on precomputed templates that can be instantiated and modified in both space and time using basic transformations familiar to many artists. At each frame, our system uses control particles to locally affect the edited liquid simulation. This strategy leads to an efficient control. We use our method to generate many examples using several types of targets. The resulting animations appear plausible and give an overview of the various types of animation that we can generate using our liquid compositing tool. Our system uses precomputed portions of liquid simulations called templates in order to compose liquid animations. Each template stores the behavior of a liquid simulation in a user-defined region of space. Once recorded, templates are stored in a database. During the recording process and for each frame, the position and the velocity of each particle located in the recorded area are stored. Global information, such as the region size or the template duration, are also stored. When editing a liquid simulation, a user selects a template and creates an instance of it in the scene in order to control the simulated liquid. Once instantiated, a template can be manipulated and transformed in both space and time using a set of transformations familiar to artists. At each frame of the simulation, these control particles are used to generate control forces in order to modify the liquid behavior and manage temporary particles in the scene. Control particles exert control forces on the liquid particles. Attraction and velocity forces, inspired by the work from Thuret and colleagues, are used for control. Each control particle, in orange, first attracts liquid particles, in blue, toward its position by exerting an attraction force modulated by the control particle coverage. When covered by enough liquid, attraction forces are reduced. Control particles also generate forces in order to reduce the velocity difference with the surrounding liquid particles. These forces are scaled down when emitted from a control particle with less liquid coverage, since they could counteract the attraction forces. These forces allow us to attract and drive a simulated liquid to make it match the template behavior. However, these forces do not exert control to reproduce the surface itself in the template. In addition to these forces, we therefore generate repulsion forces at the template surface. To do so, we first generate a layer of repulsion particles. For each control particle, we generate a repulsion particle candidate at a distance h along its negative normalized density gradient. Note that repulsion particles located too close to a control particle are discarded. The repulsion layer is generated for the whole template duration during a precomputation process when it is first instantiated in the scene. During the simulation, each repulsion particle generates a repulsion force on the liquid particles located in its neighborhood. These forces push the liquid particles toward the template surface. In some cases, the dynamics of the liquid prevents the liquid to spray into regions covered by liquid in the template. In other cases, the amount of liquid nearby may not be sufficient to rapidly drag it in to reproduce the whole template. To quickly and efficiently tackle these issues, we introduce temporary particles. At each frame and for each liquid particle inside at least one template instance, we estimate the density discrepancy between control and liquid particles. If this discrepancy is larger than a given threshold, a temporary particle candidate is seeded. Temporary particle candidates are immediately removed if they are too close to an existing liquid particle. Temporary particle candidates are also removed when too close to another candidate. The remaining candidates are transformed into temporary particles. During its lifetime, the dynamics of a temporary particle is ruled by the Navier-Stokes equations and affected by our control forces. At each frame, we update the list of temporary particles. Temporary particles are removed when no longer useful to reproduce any template. We consider that it happens when a temporary particle is not located in a control area anymore. In this case, a temporary particle becomes a candidate to removal. If the candidate is not surrounded by enough non-temporal liquid, it is not removed since its deletion would be too perceptible. Otherwise, the temporary particle candidate is removed. In order to extend the spectrum of possibilities, we allow users to apply time-varying affine transformations on each instance of a template. These transformations include translations, rotations, uniform and non-uniform scalings, as well as reflections. They can be used and combined to modify a template instance when composing an animation. Every time we want to evaluate a physical quantity in a transformed template instance at a given position, we apply the inverse transformation of the instance to this position before estimating this quantity into the untransformed canonical space. Control particle density is evaluated in the untransformed space. Similarly, attraction and repulsion forces are evaluated in the untransformed space before applying the instance transformation to get the final forces. Velocity forces are computed the same way after transforming each liquid particle velocity using the inverse of each instance transformation. In the case of a time-varying affine transformation, each control particle velocity is also virtually modified by summing the velocity of the instance at its world space position. In addition to the spatial transformations, several temporal transformations are also provided to users. First, a user can simply define when a template starts or stops in our system. The activation period of a template can also be cropped to only use a portion of it. A user can play a template at faster or slower speed. In this case, velocity of control particles are virtually multiplied by the play speed factor. A template can also be played in reverse order. In this case, the velocity of each control particle will be virtually multiplied by -1. In order to reduce artifacts due to control discontinuities at the border of a control area, we extend a Falloff area around it. In this area, temporary particles cannot be created nor removed, and control forces are reduced when moving away from the interior part of the template. An intuitive user interface has been created in order to easily and quickly compose R-directed simulations. Using the panel on the right, a user can choose a template from the database, instantiate it, and tweak its control parameters. The simulated liquid, template instances, and their respective control and repulsion particles are displayed in a viewport. Each template instance can be spatially transformed using a 3D gizmo. At the bottom of our interface, a timeline displays the range of frames of each animation. The current active frame is shown using a vertical bar in red, and the range of simulated frames currently stored in memory for fast replay is displayed using a red rectangle. Each template instance is represented in the timeline using a rectangle in lavender in its own animation track. Each instance can be selected by clicking on this rectangle representing its activation period. This activation period can be either advanced or delayed using a simple drag and drop mechanism. In this video, we replay a simulated liquid composition in which a jet of liquid jumps from and dives back to a pool. The template instances created in the scene are activated successively. The boundaries of a template are drawn in green when active at the current animation frame, or in red if inactive. This second example shows how simple it is for users to select and instantiate a template using our system. As we mentioned, template instances can be manipulated using a gizmo, a type of control already familiar to digital artists. This last video shows how a user can modify the play speed of an instance and can crop the beginning and the end of its activation period. When recorded, templates are stored as binary files in our database and are loaded once in memory, even if they are instantiated multiple times. In order to speed up particle neighborhood search, we use several uniform acceleration structures called buckets in the literature. 2 buckets covering the whole domain, one for liquid particles and one for temporary particles candidates, are used. In addition to these buckets, 2 other buckets covering each template are used for control and repulsion particles. Control and repulsion particles are stored in these buckets for the whole template duration when loaded in memory. Although we could use other Lagrangian methods to simulate our liquids, we generated our result using DFSPH from Bender and Koshir. The current version of our system has been implemented using Splish for simulation and ImGUI for user interface. Our system has finally been multi-threaded using OpenMP. We use our system to generate many control liquid animations, from which we present here a number of examples. In the first simple 2D example, we recreate the impact of a rectangular drop of water falling in a pool without inserting new particles in mid-air. We first recorded the impact of such a drop in the template before instantiating it on a calm surface of liquid. Our system correctly modified the liquid behavior of the simulation to locally recreate the drop impact and propagating ripples without visual artifacts due to the creation of a drop of water above the surface. Note that our system adds only a small computational overhead over the actual uncontrolled simulation. In this example, an average of 5.6 milliseconds are dedicated to the control out of the 190.2 milliseconds needed to simulate each animation frame. We also recorded a wave template from a wave machine-based simulation. Instantiating this template in the scene gives birth to a wave that propagates outside of the control region in a realistic way. Thanks to the Falloff area, boundaries remain smooth between controlled and uncontrolled liquid, leading to a convincing blended result. Our method is compatible with templates containing solid objects. Thanks to its layer of repulsion particles, our method generates stronger control in boundary liquid template regions. We demonstrate this aspect by recording the motion of a liquid mixed with a rotating blade and instantiating the resulting template in order to reproduce its dynamic and surface. We ran a similar experiment in 3D. After recording the behavior of a liquid mixed with a rotating blade, we create an instance of this template in a calm surface of water. Similarly to our 2D experiment, our system efficiently and correctly reproduces the template in both space and time. The liquid spins away from the center, creating a hole and partly circular expanding waves. Our method is compatible with templates simulated under different physical properties than the ones of the control liquid. In this example, we recorded a viscous honey-like liquid motion before instantiating the resulting template in the scene in order to control a water-like liquid. In this example, the template has been scaled up by a factor of 2 and flipped upside down in order to make a buckling pattern rise from the surface. Although a viscous liquid and water exhibit very different behaviors, our system correctly drives the water simulation in order to recreate the buckling pattern. Our system is compatible with the control of multiphase liquids. In this example, we created two instances of the same jet of water, each of them controlling a different phase of a two-phase liquid. The two liquids jump out and dive back in the simulation domain with unexpected behavior. After recording water-filled letter shapes falling and splashing at the bottom of a simulation domain, we instantiated the templates in a scene, playing them from the end to the beginning. Our method efficiently reproduces the animation, drawing water from the simulation domain to recreate the letters. In our system, a control liquid can interact with rigid bodies. In this last example, a hand made of water raises up a floating boat in the air. With a strategy similar to the one used in the previous example, a water-filled hand shape has been recorded, falling and splashing in an empty scene. The template is played in reverse order while controlling the liquid in order to make the hand emerge from water. In the simulation, the water from the hand interacts with the boat using a classical two-way coupling method. During this talk, we presented an intuitive and easy-to-use tool, allowing a user to compose SPH-based liquid simulations using precomputed liquid templates stored in a database. Control forces and temporary particles are used to efficiently reproduce the templates instantiated in a scene. Our control strategy is efficient, leading to a small computational overhead. The resulting system is easy to use, robust, and efficiently generates predictable R-directed simulations. In the future, many extensions and improvements of our system could be added. First, going from CPU to GPU implementation should deliver reasonable gains since our control strategy could be efficiently parallelized. Our system is not designed to handle transformations involving large scaling factors and side effects can appear. Our method should be improved to robustly handle more extreme deformations. The placement of template instances is sometimes a little challenging in order for them to be seamlessly integrated in a liquid. Automatic positioning and refinement of control parameters over time could be a nice improvement. Last but not least, more complex ways to combine templates should also be found, allowing a user to subtract templates instances or attach them to some fluid features. Thank you for your attention. If you have any questions, do not hesitate to ask.